Okay, so a titration is a procedure in which you can determine the concentration of an unknown solution. All right, and like I was saying, if we were we actually will do a lab, or we would have done a lab, a titration lab, in which we find the concentration of an unknown hydrochloric acid solution. Okay, and basically what you use is you use a known volume and concentration of one of the reagents, and you use a known volume of the unknown, and you basically are finding the concentration of the unknown. So for your known, you will know the amount you used, and you will know the concentration, which is in molarities. And remember, our amount is in liters, and the concentration is molarities. So if I multiply these, what do I get out of that? If I multiply a liter times a molarity, we get moles out of that. Yep, exactly. We get moles. Which, remember, that's what we want to get. And then for unknown concentration, we will know the amount that we have used. We will know the amount we used. And from this information, from how many moles of the known I used, that will tell me how many moles of my unknown I have. And if you take that number of moles and you divide it by the volume, you can find the molarity. But one of the things that you have to do in a titration is you have to be able to find a reaction in which they react, and you have an indicator that tells you when the reaction is done. Okay, so like for example, if I have compound A and I'm reacting it with compound B and I form the compound C. Let's say I don't know the concentration of compound B. Okay, so I'm looking for the molarity of compound B. Okay, but I know everything about A. I know the molarity. I know how much of it I used. All right, and what it basically is doing is I'm doing a reaction and forming C. However, this has to give me an indication when the reaction is done. Indication when reaction is done. Because when it's done, that implies I have equal amount of moles of A and B. So it's telling me, okay, the reaction is done, so I can stop and I'll know exactly how much A I've used, and since I know the concentration, I can figure out how many moles of B. All right. So for acid-base titrations, this works very well. Okay, so if I'm finding an unknown concentration of an acid, let's say I don't know the concentration of hydrochloric acid. Okay, so I'm going to use a base like sodium hydroxide in order to do a reaction, because I know in the equation sodium hydroxide plus HCl, this is a 1-to-1 ratio. If I balance the equation, everything's 1-to-1. However many moles of sodium hydroxide I use, that equals the same amount of moles of hydrochloric acid I use. So if I have 12 moles of sodium hydroxide, I need 12 moles of HCl to neutralize 100% of my sodium hydroxide. However, I need an indicator in order to tell me this. Okay, and we actually do have acid-base indicators. Okay, either like a pH paper. We actually do a lab prior of this lab where we actually do a lab of indicators, and we find all about it. And we do a lab about it so that you can learn about indicators, and then the following week we do this lab with the indicators. Okay, so remember, this is a neutralization reaction. So as soon as I'm at a pH of 7, what does that mean? My moles of acid equals my moles of hydroxide. I have equal amount of moles. So I need an indicator that tells me when I'm at a pH of 7. Okay, and we actually have an indicator. It's called phenolphthalein. It's an organic molecule, and it's clear when we're in acid, and it turns pink when we are in base. All right, so when we are underneath, so less than a pH of 7, it's clear. When we're greater than a pH of 7, it turns pink. So what we do is we put the unknown hydrochloric acid in here, and it's clear, and we drip in our sodium hydroxide. All right? And as soon as this turns pink, like right when it turns pink, I know I'm pretty much at what is called the equivalence point, when I have exactly equal amounts of my sodium hydroxide and my HCl, and based off of the amounts, I can go back and I can calculate the molarity of my unknown. Okay, so that's basically how a titration works. I think there are some pictures here. I'll show you the pictures, and then we'll go over these calculations. Okay, so a base of known concentration is added from a burette to the flask containing the unknown HCl concentration. So our HCl's in here. This molarity is unknown. However, I know the amount I use. It looks like they're using 100 milliliters, maybe. Okay. In our burette, which is this thing here, I have sodium hydroxide. I know what the molarity is. All right. Let's just assume it's 0.01 molar. And then on the burette, they don't show this, but it's marked. I have, at the top it's 1 mil, and then 2 mils, and then 3 mils, 4, 5, 6, and I drain it down. And as soon as I hit the equivalence point, I record how much of the sodium hydroxide I added. So that will tell me its volume. So if I know the volume, so here's the volume. Let's say it's 3 milliliters, and I know the molarity of it, I can figure out how many moles it took in order to hit the equivalence point. And however many moles of sodium hydroxide it took, that's also exactly how many moles of HCl I have in there, because it's equivalent. The number of moles of H plus is equal to the number of moles of acid, because this is a 1-to-1 ratio. If this was a 1-to-2, if I balanced it and it's 1-to-2, it would have to be twice the amount, and I would have to do a mole-to-mole conversion. All right, so again, there are problems on here that we'll talk about. But for right now, I have a known amount of sodium hydroxide in here and an unknown molarity of HCl. Okay, so the point in a titration at which all the acid has been neutralized is called the equivalence point. I don't know if you can see it, but this solution is slightly pink. You guys able to see that? So here it's clear, it's colorless, and here it's slightly pink. All right, that slightly pink is implying I'm just above a pH of 7, or pretty much I'm pretty much equal at a pH of 7. So that's implying I hit the equivalence point. And it's kind of showing you here. You see here I have acid. I have an acid molecule. I got an acid molecule. So in here it's acidic. Maybe it's like a pH of 2 because I have HCl. And then I drip in my sodium hydroxide, and the hydroxide reacts with all the acid, and eventually it's all neutral. You see how it's all water now? I don't have acid or base in there, and the way I know that is because of the indicator. If I did not have an indicator, I would not know when I've reached the equivalence point. So when you do a titration, you have to have an indicator for that reaction that will tell you when you have hit the equivalence point. So you can't always do a titration on everything. It really only matters if you have an indicator that will indicate when you have hit the equivalence points. Okay, does that make sense? All right, so here are some problems. So does that make sense, or do you guys want me to kind of go over it again?
Is titration the dropping?
This whole process is called a titration. A titration just basically means you are using you're doing a chemical reaction in order to find the equivalence point of a reaction in order to figure out the unknown concentration of a compound.
Steve, could you go over that last slide again? Just the process?
Yeah, I'll tell you what, I will. We're going to do this. I'm going to draw it out here. So let's pretend we're actually doing a titration. So this is what we do in lab. I give you sodium hydroxide. I tell you that we have a bottle of sodium hydroxide and it's 0.1 molar. Actually, you know what? Let's make it 1 molar just so the math while I'm going over the math, it'll be easier. But in lab, we actually do 0.1 molar. Let's just say it's 1.0 molar. Okay? And then we have hydrochloric acid. We have a bottle of hydrochloric acid. We don't know what the molarity of this is. This is what we're trying to find. Let's actually do this in green so that we can follow everything. So the HCl will be in green. This concentration, I don't know. Okay? So the way that we set this up is in our Erlenmeyer, I put in a total of 10 liters. Again, I'm just making the math easy. It's really milliliters, but let's just make it easy. 10 milliliters of hydrochloric acid. So I know exactly how much acid I've put in here, but I do not know what the molarity is. That's what we're trying to find. Okay? And then in the burette, here's our burette. Here's our burette. Okay. It starts, it's 1 mil here, 2 mils, 3 mils, 4 mils, 5, 6, 7, 8, 9, 10. I think it goes to 50 mils. All right, let's just do 5, 6, 7, 8, 9. And I fill this up. Let's do this in blue. I fill this up with my sodium hydroxide. And I fill it all the way up at the 0 mark. Or I should have a 0 mark here. 0. Okay? So this is filled up with this, our sodium hydroxide, 1 molar. And my unknown HCl is in here. Okay? Then I take my indicator, my phenolphthalein, and I drip a drop or two into our hydrochloric acid. All right, now it's going to be clear. This starts out as clear. Okay. Then what I do is I start dripping in my sodium hydroxide. All right, I drip it in, I drip it in, I drip it in. Eventually, at some point, what's going to happen is this is what it's going to look like. All right. I now have my Erlenmeyer flask. Okay. And this is going to be it's going to be a very light pink in color. Okay, so it starts out clear. Here's actually, it starts out like this. Until I'm getting messier now. And then I drip in my sodium hydroxide, dripping it in and dripping in. And then, at a certain point, it's going to turn that very, very faint pink. And I drip it in very slowly. And let's say that was at 12 milliliters. It took 12 milliliters of the sodium hydroxide in order to hit the equivalence point. So I'm now at the equivalence point. All right, does everyone follow me so far? I mean, all I do is I start with exactly 10 mils of HCl. I don't know the concentration. I put in the sodium hydroxide. I mark it up to 0. So I fill this all the way up to 0, 1 molar, and I drip in and drip in and drip in, and eventually this clear will turn into a pink color. And right when it turns pink is when I stop, because that's the equivalence point. That means I have equal amounts of H plus ions into hydroxide ions. Is that good so far? Do you understand it? Okay, good. So now, the whole point of this is to figure out what our molarity is. Okay? And the molarity of the acid, remember, the molarity of the acid is the moles of the H plus ions divided by the liters of how much I used. Which that I know, it's 10 mils. I started with our 10 mils. I'm sorry, our 10 liters. The moles of H plus is what all of this is all about. Okay? So remember, I started with, let's actually change this into liters, just to make the math easier. It doesn't matter if it's milliliters or whatever. I just don't want to, I'll convert everything. Okay? So in order to find out how many moles of sodium hydroxide I use, remember, this is our sodium hydroxide. If I find out how much sodium hydroxide I use, remember, that's equal. If I use 3 moles of sodium hydroxide, how many moles of acid are in here? You guys can type it or say it. 3, exactly, it's equal, right? Because in this reaction, if I take HCl and add it to sodium hydroxide, I get H2O and NaCl. This is a neutralization reaction. And if you balance it, it's a 1 to 1. For every mole of this, I need the exact same number of moles of that in order to neutralize it. Okay? So the molarity of sodium hydroxide is 1.0, and the volume is 12. So I use 12 liters, let's say 12.0 liters. I'm going to multiply it by the molarity, because remember the molarity is moles over 1 liter. The liters cancel out, so that means I have used 12 moles of the sodium hydroxide. So since 12 moles of sodium hydroxide was used, how many moles of HCl is in here? You guys can... 12. Yep, good, exactly. It's the same number because it's equal. Based off of our balanced equation, it's equal. All right, right here I said for however many hydroxide I have, that's how much H plus I have. So that means my unknown solution had 12 moles of H plus ions in it. So now I take this 12 and I plug it into there. So it's 12 divided by 10, right, which is what? Is 1.2 molarity. So the molarity of my unknown solution is 1.2 moles. And that's basically what a titration is and what a titration does. I have my two reagents. I have my sodium hydroxide here, my HCl here. I've put in an indicator that tells me when I hit the equivalence point, because without that, I would have no idea when I'm supposed to stop. Like, when am I supposed to stop? If I don't have anything like telling me I have equal amounts, then I have no idea. That's why acid bases are really good for a titration, because we've got indicators that tell us when we're exactly at a pH of 7, where we have equal amounts of acid and base. So as soon as I hit that indicator, I figure out, based off of our burette, how much I've used. However much I used, I multiply it by the molarity of that, and that will tell me how many moles, which then, in turn, tells me how many moles I had here, which then I can figure out our molarity. Okay? So did that explain it better? Okay, so this first problem, okay, if 25 mils of HCl solution requires 46.3 milliliters of a 0.203 molar sodium hydroxide solution to neutralize, what is the concentration of the HCl? All right, so this is that exact problem that we just did, except our numbers are a little different. Okay, so I'm using 25 mils of HCl, so I know I have 25.0 mils of HCl. I'm looking for the molarity of this HCl. Okay, and it's telling me that I used 46.3 milliliters of 0.203 molar sodium hydroxide. So when it hit the equivalence point, this is how much of it took. Okay? So basically what you do is you take this information, because remember, this information I can find moles. So, but you got to remember that you have to convert to liters. So you have to convert everything to liters. So 0.0463 liters of sodium hydroxide. Multiply that by the molarity. So 0.203 moles of sodium hydroxide is to 1 liter of sodium hydroxide. So if we do that, calculate it real quick. 0.0463 times 0.203. So I get 0.0093, let's just round this up, 99 moles of sodium hydroxide. Okay, sorry about that little blip. I don't know why it does that. So that's how many moles of sodium hydroxide. So how many moles of acid is it? It's the same amount. So that's also how many moles of HCl I have, or H plus ions. So I'm going to take that number and divide it by its volume, which was 25 milliliters. And that will tell me the molarity. So 0.37, how many sig figs should we do? 3 sig figs. 6 molar. All right? That makes sense? It should be right there. 0.376. Okay? Questions on that? I want to do the next one because it's a little different. I'm going to do it on the other board. That's basically how you do them. It's basically you are using information from the titration in order to find the information of your acid. Okay, this one's a little different because notice it's H2SO4. So if you write the equation, so H2SO4 plus sodium hydroxide gives you H2O plus Na2SO4. And this time you have to balance the equation. So basically, you need 2 moles. All right, it's 2 moles, and I think I'll put 2 here. It's a 1-to-2 ratio of your acid versus your base. So you have to make sure that you factor this into your equation. Okay, so see, it says here, so this time it's 25 mils of H2SO4. Okay, requires 46.3 mils of the 0.2, and so forth and so on. Okay, so if you go back in the slide, I'll show you where. So if you look here at the put this down. So if you look at the balance equation, see how it's a 2-to-1 ratio. All right. So right here, you have to use a mole-to-mole conversion. For 1 mole of H2SO4, there are 2 moles of sodium hydroxide. Okay. So when you figure out the moles of sodium hydroxide, everything is the same. Okay. But when you find your moles of your H2SO4, all right, you have to remember that for every mole of sodium hydroxide, there are 2 moles of the sulfuric acid. Okay, so it's going to be twice the amount. It will take twice the amount of sodium hydroxide in order to neutralize 1 equivalent of our sulfuric acid. Okay, so going back here, just kind of do these problems again. So 0.0463, that's liters of your sodium hydroxide. All right, and then this is your molarity, 0.203 moles of sodium hydroxide to 1 liter of sodium hydroxide. So that moles to moles stuff is with us forever. Okay, because you've got to remember that this is still how many moles of sodium hydroxide you formed. And remember, this is moles of NaOH. In our last example, it was a 1-to-1 ratio, so I didn't worry about it. Okay, but when you have something like this, where it's not a 1-to-1, you do have to worry about it. So now I do my mole-to-mole conversion. For every 1 mole of sodium hydroxide, it's 2 moles of the H2SO4. Right? H2SO4, yeah. Right. Because you have 2 H's for every one. Oh, equal times 2. 0.01879. Just put that. I'm running out of room here, so I'll just do it on here. Oh, actually, you know what? I think they did that wrong on there. It's supposed to be divided by. Yeah, it's divided by. I was looking at that. I was like, that doesn't look right. This should be 1 over 2. Sorry about that, guys. Their answer is right, but they put it incorrectly into here. Yeah, it's a 2 to 1. It's 2 moles. So you should have a 1 here. Yeah. Yeah. That should be a 1 there, and that should be a 2 there. Because what you've done, is you have twice the amount of sodium hydroxide. So 0.009399 divided by 2. Yeah, there we go. 0.0046995. That's your moles. Divided by your volume that you use, which is the 25 mils. So 0.025. And you get 0.18 molar. Okay? So yeah, in this slide is incorrect. That should be 1 over 2. I can't change it. I'm telling you, this publisher makes a lot of mistakes. That should be 1. That should be a 2. Okay? Okay, so, that said, why don't we just do a problem? Let's, let me put a problem here for you guys, and you guys do it one yourself for practice. You should write them in angry. You know what? I don't like to be angry. I know I'm right. All right, let's see. What should we do here? What's the molarity of 30 mils of phosphoric acid if it took, let's see, how about 52 mils of a 0.513 molar solution of sodium hydroxide to neutralize. All right, what is the molarity of 30 mils of phosphoric acid if it took 52.0 mils of a 0.513 molar solution of sodium hydroxide to neutralize it? All right, I'll give you guys a little bit of time. Okay, so the first thing you need to do is write a balanced equation. So take your sodium hydroxide. I mean, you don't necessarily have to all the time. It does help, but by looking at this, so notice I have 3 H's for every mole of here, right? So how many sodium hydroxides is it going to take in order to neutralize all of the phosphoric acid? I mean, so if you think about it that way, right? So for every mole of H3PO4, I've got 3 H pluses. Right? For every mole of sodium hydroxide, I only have 1 hydroxide. Right? So 1 mole of this will neutralize 1 mole of this. So I need 3 of these in order to neutralize 1 mole of my H3PO4. So I know that I'm going to need a 3 there. So even if you don't balance the equation, you still know how many of these you need based off of how many H pluses I have. Okay? So I don't know if that helps or... let me erase these. Okay, so start with the information that you're given. You're given 52 mils of 0.513. So 0.052 times your 0.513. So remember that's moles over liter. And that number is 0.026676, and that is moles of sodium hydroxide. I got to convert this now into moles of phosphoric acid. So I know there are 3 moles of sodium hydroxide for every 1 mole of phosphoric acid. Right? Because this number, remember, is going to be 3 times the amount. Right? Because it takes 3 of these for every 1 of these. So I'm trying to find out how many moles of this there are. So I got to take this number, because that number is the sodium hydroxide, divided by 3. It's basically what I'm doing. Because this is 3 moles of these, I need to find how much is for 1 mole of that. So that's why we do that division. So 0.008892. And then you're going to divide this, because this is now moles of H3PO4. You divide it now by your volume, 0.030. And you get 0. Can't remember my writing. Is that a 2? 296? Does that agree? Or is it a 796? What do you guys get? I think it's 296. Yeah, it's 296.
Got it.
Good. 296. Perfect. Good on. Okay? So still mole-to-mole conversions, but basically it's a titration. You're basically, I mean, it's just the whole point of a titration, doing these calculations. All right? All right, let's now, any questions? Otherwise I want to talk about a buffer, which is the last part of this chapter. Okay, so let's talk about a buffer. Buffers is basically a solution of a weak acid and its conjugate base. Those right there. It's a solution of a weak acid and a conjugate base that prevents drastic changes in pH. Okay, so a buffer, it's basically this. Let's say I have a solution. Okay, actually, yeah. Let's say I have a solution of water. Say it's water, so I'm at a pH of 7. And I add in here hydrochloric acid. All right? I drip in hydrochloric acid. What is the pH after I add in the hydrochloric acid? Well, the pH is going to be, a pH of like 1 or 2, because hydrochloric acid is a strong acid. Let's say now I have a solution, but it's a buffered solution. It's buffered. If I take that HCl now and I drip in a few drops of it, okay, and let's say this is at a pH of 6 with our buffer in it to the pH of 6, and I add in my hydrochloric acid, it stays at a pH of 6. It doesn't change because I have the buffer in there. The buffer, in a way, it cancels out any additional acid that is being added in there. Let's say I add in a little bit more HCl. What happens? Well, it's still a pH of 6. All right, because I have the buffer in there. There is a certain point where I'm going to start adding in a lot of HCl. And once I add in a lot of HCl, it overcomes our buffer. And then I will be at a pH of 1. However, up until that point, basically any acid I add in here, the buffer, it kind of absorbs it. It kind of it gets rid of all that excess H plus ions. That's basically what a buffer is. Our blood has a buffer. Our blood's roughly a pH of like like 7.2 or 7.3. Anytime that we have an increase in acid or base, our blood actually has the buffer, is able to actually remove any of that extra acid. At a certain point, though, if your body keeps producing a lot of acid, then it overcomes your buffer, and you now have some serious problems. Okay, but that's basically what a buffer is. It's a mixture of a weak acid and a base, and it removes any excess H plus ions. Okay, and this is kind of just to kind of show you how it works. So here it's originally pH of 7. They add hydrochloric acid into it. Again, it's pure water, so this is the exact example I showed. And you now are at a pH of 3.3. In a buffer solution, you start at 4.74. You add in the HCl, and it roughly stays around at that same value. Okay. So let me talk about what's actually happening at the atomic level, the chemistry of it. The book doesn't really talk about it too much, so I kind of want to show you. First of all, we said it's a weak acid and its conjugate base. So let's talk about why it's got to be a weak acid. It can't be a strong acid. So our buffer is a mixture of the two. Let's take acetic acid, which is vinegar. So if you guys remember, acetic acid is vinegar. It's a weak acid. The formula is HC2O3O2. Is that right? 3, yes. Okay, and its conjugate base has a sodium in place of the hydrogen. So it's sodium H2H3O2. For short, I'm going to write it like this, HAC and then AC minus. Just for short, because I don't want to keep writing all these all over again. And the reason it's AC minus is because it's the acetate ion has a minus charge, and the sodium is our counter ion. But the sodium is a spectator ion, so I'm not going to include it in here. All right. So our buffer is a mixture of the acetic acid, the weak acid, and its conjugate base. All right. Now, why do we use a weak acid and base? Well, you guys remember the lecture I gave you about the equilibrium? We talked about this yesterday in the slides, where if you take a weak acid, so HAC, remember, it ionizes into H plus ions and AC minus ions. Actually, you know what? Yeah, we can keep this open. All right, so it ionizes into H plus ions and AC minus ions. But remember, at a certain point, as soon as I create a lot of this reaction starts reacting and it starts reforming HAC. Okay, so at a certain point, I hit equilibrium where the forward reaction is equal to the reverse reaction. After I make a certain amount of this, these now start reacting and start reforming HAC. And remember, what makes our pH and something acidic is the amount of H plus ions. The more H plus ions I have, the more acidic. The less H plus ions I have, the less acidic. So once I hit a certain level of H plus ions, or pH, they start reacting and start reforming our HAC. Okay? So that's basically why we need to have a weak acid and a weak base. Because what we actually do is, in a buffer, I actually add more of this in here. Okay? So a buffer is a mixture of the HAC plus H plus ions, plus a lot of these AC minus ions. I add more of this in there, AC minus. So imagine I've added a lot of this in here. Okay? So this is basically our buffer. Okay? I have a small amount of HAC, I've got H plus ions, and I have a lot more of these AC minuses because I added these into it. Because it's not just a mixture. It's not just our acetic acid. It's our acetic acid plus our AC minus in the form of sodium acetate. Well, if I were now to add acid into here, so here is let's imagine I have my beaker, and I have this in there. All right, so I have a mixture of the HAC, the H plus, and all these acetate ions. Let's say now I start adding acid into here. So more H plus ions. Okay, so the whole point of a buffer is that it does not increase our pH. It keeps it the same. So these extra H plus ions must be all consumed. Okay, so how do you think that's doing it? Well, what's happening is as soon as I'm adding the H plus ions, these extra acetates I have around, they grab that H plus ion and form it into the HAC. It drives the equilibrium all towards the HAC, and it removes any extra H plus ions I've added in there. So I don't change how much H plus I have. Remember, this is responsible for our pH. Okay, so let's say I have a pH of 4.2. If I add more H plus into here, I would expect that to actually go lower. However, the extra acetates around are grabbing that H plus because our equilibrium says I can only have a certain amount of these in there. So any extra H plus added in there, it gets carried through and I start forming HAC. So in turn, the acetate ions are removing that extra H plus ions, and it keeps our pH exactly where it is. So if I add more H plus and more H plus and more H plus, again, more of these acetates are pulled away. Eventually, what's going to happen? I'm going to add enough H plus in here that I no longer have any more of the acetates in there, and I start increasing the amount of H plus ions. Okay, so our buffer is not, it's not always there. It's really however much of the acetate ions or our conjugate base. It's how much of our conjugate base I have in my solution that I have a buffer. As soon as all of it has been removed, because I've added a lot of H plus, I don't have a buffer anymore. Okay? So that makes sense as far as how a buffer works. And that's why it has to be weak, all right? Because weak acids and bases have an equilibrium. Strong acids and bases don't. So I can't make a solution of hydrochloric acid and Cl minus, right? Because if I take HCl, I throw it in water, I get 100% of H plus and Cl minus ions. I do not have an equilibrium. I just have this. So if I add more H plus into here, it just increases my H plus. My chloride ion will not grab any of these H plus ions. It doesn't do anything. It just increases my H plus. But in the weak version, because I form this equilibrium, these will grab the H pluses and form the acid form of it. Okay? Any questions?
How can we know if it will make an equilibrium or not?
If it's an acid base. If it's a weak acid. So we talked about yesterday the list of strong acids. So if it's not one of the strong acids, it's a weak acid.
And that's, okay.
Yep. So here are examples. So will HCl and sodium chloride make a good buffer? Will these make a good buffer? So the question is HCl a strong acid or is it a weak acid? And what do you guys say? Well, first, is HCl a strong acid or a weak acid? You can put S for strong or W for weak. You guys remember? Anybody?
No, I don't have the list on me.
Well, what do you guys think? It's hydrochloric acid. Like, that's one of the things. Yeah, it's a strong acid. Exactly. Yep. Yep. Yeah, so it's a strong acid. So since it's a strong acid, so remember, guys, the list was HCl, HBr. So it's the halogens, with the exception of HF. Nitric acid, sulfuric acid. If you guys remember, I always said that I forget between chloric and perchloric, and we found out it's both. That's why I was like, well, I'm right half of the time. So these are the strong acids. So these will not make a buffer. Anything other than that will make a buffer. Okay? So the mixture of HCl and sodium chloride, not a good buffer. Not a good buffer. In fact, it won't even make a buffer. What about NaF and KF? A mixture of NaF and KF. Put yes, it's a good buffer, or put N, it's not a good buffer. Okay, so Kimberly says yes. Anybody say anything else? Anybody say no? Anyone say yes? Got a bunch of people in here. I'm only getting Kimberly. If you guys don't say I don't know, then put a question mark. At least I know that you guys are here and, or listening or something. Anybody? Again, I got an answer from Kimberly. Are you guys there? Is this thing on? All right, yeah, okay. So, okay, so you guys said yes. So remember, what makes a buffer? Weak acid and its conjugate base. All right, which one of these is the acid? The answer is none of them are an acid. So this would not be a buffer. Buffer has to be a weak acid and its conjugate. Oh, yeah, there you go. Good, there you go. Yep. Yeah, at first it's like, oh yeah, these are perfect. But one of these has to be an acid. So if I had like HF and KF, or if I had HF and NaF, then these would be a buffer. Right? But in this case, notice it's NaF and KF. That will not be a buffer. It has to be a mixture of the acid and the base. So this one would be a good buffer because we have the weak acid plus we have a conjugate base form of it. Okay? Okay. Okay, so HCl strong, it wouldn't be, there's no acid present, so it wouldn't be an HCN is a weak acid and the CN is the conjugate base. Okay? We will not be doing any of the pH calculations with a buffer, so this stuff on the slides you can ignore. And that is the end of the chapter.